How's it going, everyone? Here I'm going to explain a phenomena that you might have experienced, you might have heard of, that the horses on the outside of a carousel go faster than the horses on the inside of the carousel. And it's absolutely true. It's not a myth. If you've experienced it, it wasn't all in your head. It's actually the truth. And it might seem counterintuitive because, well, the horses are on the same platform, right? If this is the platform of our carousel right here, right? It's like a ring shape. It's rotating. All the horses are attached to the same ring as it rotates. How could the ones on the outside be moving faster than the ones on the inside? So to explain that, we have to talk about the difference between how we usually define speed, which is distance over time, right? Like meters per second, miles per hour, kilometers per hour, and angular speed or angular velocity, which is not distance over time, but how much rotation occurs over a period of time. So if you imagine two horses, one on the inside and one on the outside of a carousel, they are beside each other. As the carousel rotates, they remain beside each other. Okay, let's say it rotates 90 degrees. They are beside each other. Let's say it rotates, it's gone 180 degrees. They're still beside each other. 270 degrees. They are still beside each other. Carousel does a full rotation, 360 degrees. They are still beside each other. They were beside each other the whole time. It took them the same amount of time to do a full rotation, however long it takes the carousel to do one rotation. It took them the same amount of time to do one rotation. And that's key. Their angular velocity is the same. Same amount of time to do one rotation. But how much distance do they cover in that rotation? What is their path length? Look at the inner horse. It traveled the path of the inner circle, the smaller circle. What did the outer horse do in that same amount of time? It traveled the path of the outer circle, the larger circle. Okay, that's a longer path. It is a bigger circle that outer horse trots out. If you cover a longer distance, you cross a longer path in the same amount of time as someone else who covered a shorter path, well, that's a larger distance over time. That's a greater speed. Higher distance over time, higher speed. The outer horse is moving faster. Okay, now let's add some numbers to this illustration, okay, to make it a bit easier to imagine. Okay, let's say the distance from the center of the carousel to that inner horse, let's say that's 3 meters. And the distance from the center to that outer horse, let's say that's 6 meters. So if you like thinking in feet, that's approximately 10 feet versus 20 feet. Pretty typical dimensions from a carousel, right? Like some are bigger, some are smaller, but that's reasonable dimensions, okay? So what's the circumference of that inner circle, okay? The path that the inner horse trots out. Well, circumference is 2 pi times the radius, okay? And in our case here, the radius is 3 meters, right? So 2 pi times 3. Pi is approximately 3. And the mathematicians will hate this. The physicists will love this. Okay, 2 pi times 3, that's approximately 2 times 3 times 3, 2 times 9, that's about 18 meters. That's the distance that inner horse trots out. And let's say the time period, okay, capital T is used often in physics for period. That's the time duration of one cycle, one rotation. Let's say it's 30 seconds, okay? So it takes you 30 seconds to complete a full circle, okay, around this carousel. So the speed of that inner horse is the path length divided by the time period, so that's 18 meters divided by 30 seconds. 18 divided by 30 is 0.6. Okay, 0.6 meters per second. That's the speed of that inner horse. Now what's going on with the outer horse? Okay, well, the circumference of the outer horse, 2 pi times the radius. It's the radius of the from the center to the outer horse, right? So that's 6 meters. So we have 2 times pi times 6. Again, pi is approximately 3. So 2 times pi times 6, it's about 2 times 3 times 6. That's going to be about 36 meters. Okay? What's the speed of that outer horse? Well, that's going to be the path length divided by the period, the time duration of one rotation, which is the same, right? Because like we discussed, they have the same angular velocity. It takes them the same amount of time to make one full circle. Of course it does, because they're on the same platform. Okay, so we have 36 meters divided by 30 seconds, and that is going to be 1.2 meters per second. Okay, so that outer horse is moving at 1.2 meters per second. The inner horse is moving at 0.6 meters per second. The outer horse is moving faster. But how much faster? A lot faster. Okay, let's look at the ratio between these two. The outer horse speed divided by the inner horse speed. Okay, S0 or SO divided by SI. That's 1.2 divided by 0.6, right? That is 2. That outer horse is moving twice as fast. Twice as fast is huge. That's the difference between 50 kilometers an hour and 100 kilometers an hour, which is the difference between driving through a residential area and driving on the highway. Now, every carousel is a little bit different. Not every carousel has these exact dimensions, but as we discussed, these are pretty typical dimensions for a carousel. It's reasonable, right? The width of that platform that they're on is about 3 meters, right? The most outside horse is about 6 meters from the center. The most inside horse is about 3 meters from the center. Pretty reasonable dimensions. So it's pretty reasonable that the outside horse will be approximately moving twice as fast as the inside horse. Twice as fast. And you can feel this. You can feel this because now if you're just looking forward the entire time, right? You're sitting looking forward or you're sitting looking sideways. What you're looking at is going to change at the same rate because what you're looking at depends on your perspective, which is based on what angle you've rotated. The angular velocity is the same. So the rate of what you're looking at will change the same, but there's other ways you can feel your speed. For example, how much of an acceleration you feel when the carousel first starts moving from 0. That outside horse is going to speed up to a higher velocity. So you're going to feel more of that jolt pushing you forward. How hard do you feel the wind blowing at your face? Okay, because you're moving faster through the air on the outside horse, you will feel more of that wind. There's another way you could feel it as well. Okay, take an outside observer. Let's say someone is standing and waving at you. Okay, so let's erase some of this inside stuff so it's going to be a little bit easier to look at. Okay, let's say you are looking at someone right here. Okay, and let's say you are on the inside horse. So the distance between you looks like that. Now, once you've done a quarter of a rotation, so 90-degree rotation, okay, the distance between you looks like that. You are now farther away, as expected, and you're a little bit farther away. Now we can calculate exactly what this is, right? If this is 3 meters, right, and this is 6 meters, you can define this as being 1 meter if you'd like, okay? You can use Pythagorean theorem. I won't do the calculation here, but you can calculate exactly how much farther you will be away from this person after a quarter of a rotation. Now, what if you're on the outside horse? Okay, well, you start off this far away from them, and after a quarter of a rotation, which is the same amount of time, you are now here, and this is the distance that you are away from them. Look at how much longer that yellow line is, the longer one, compared to the short yellow line, versus the difference between the two green lines. Okay, you're increasing your distance from them at a much greater rate if you're on that outside horse. You'll see them zoom by you as you're staring at them much faster. Now, we can show this without using specific numbers, right? So the speed of the inner horse is the circumference of the inner horse divided by time, which is 2 pi r of the inner horse, radius of the inner horse divided by time. And the the speed of the outer horse, circumference of the outer horse over time, which is going to be 2 pi radius corresponding to the outer horse over time. So when we take the ratio of the two, SO over SI, right, you have 2 pi RO over T divided by 2 pi RI over T. And we can rewrite this as 2 pi over T times RO divided by 2 pi over T times RI. The 2 pi over T cancels out, and you just have RO divided by RI. The ratio between the speeds is going to be equal to the ratio between the radiuses. If your radius is twice as much for the outer horse compared to the inner horse, well, then the speed is also going to be twice as much. Okay, and of course, RO is going to be bigger than RI, right? Because that's the outer radius. So that outside horse is always moving faster. So, I hope you enjoyed that. And until next time.